Okay, I'd like to all welcome you to the student seminar today. This is Luke Odell, who's been a student here since about 2011 or 12.
13.
Was it 13? He was a student here before that, too. He was a student here in the 453 class when he was actually going to Leeds in England, and then he went back, but then he came back again in 13 and started working on the hurricane project, which he's been working on, or a tornado project, which he's been working on since then. He's done a lot of things, and he's actually quite well-rounded. He's a scientist, a tornado expert, and he's a tornado chaser, kind of a celebrity. They had a special on him in England a year ago or two. Yeah, and he's also an entrepreneur with Netflix stuff. So we can get into that some other time.
I think so, yeah.
But Luke.
All right. Thank you very much, Greg. And I know this is usually saved for the end, but I wanted to give a special shout out to Addison Frederick. Decided to add her as an author on this presentation. She's spent the last 3 days without sleep trying to get trajectory analysis to work for me. And so it's been fruitful, yet we're not quite there yet, so I'm going to show some preliminary results regarding that, and hopefully for Severe Local Storms Conference in Vermont that I'm going to next week, we should have some good stuff for that. So thank you guys for coming out. I'm going to talk to you about one of my favorite things in the world, Supercell Thunderstorms. They're obviously very beautiful, but very destructive at the same time. So they're definitely particularly fascinating to me. So just a brief outline of what I'm going to go through today. I'm going to briefly introduce the research that we do upstairs on the 14th floor. We're going to have a quick look at the background of supercell dynamics. I don't want to lose people in some discussions later on when I'm showing you a bunch of images and things like that. I'd rather that we go through it at the start. And obviously, if you've got any questions, do stop me and let me know. I'll go through some motivation behind the research that we're doing, looking at the shortcomings of current theories in the literature, and look at different environments that are characteristic of tornadic and non-tornadic thunderstorms. And I'll throw a bit of storm chasing in there too, keep it lively, and really talk about kind of what I've learned from being in the field and chasing these things. So the results really largely consist of a theoretical investigation that was recently submitted to the Journal of Atmospheric Sciences, and then the application of the theory that was developed in that study. And right at the end, as I mentioned, the trajectory analysis, we've got a couple of plots to show you that are quite interesting. So in broad terms, what we do upstairs in Tripoli's group is look at numerical studies, numerical analysis of thunderstorms, supercell thunderstorms, and their processes that produce or lead to tornado-like vortices within thunderstorms. And so to do this, we set out with the plan of trying to understand the dynamic structures that develop within supercells that can ultimately support and lead to mechanisms generating tornadoes. So this is just a brief loop on the left here. This is a radar loop from a Doppler on wheels radar that was collected during the Vortex 2 experiment. This is in Goshen County, Wyoming. And this is the development of a tornado from radar reflectivity at close range. And on the right, we have a numerical simulation that we did of the same event. What you're seeing here is Goshen County here in the middle. You can see a lot of upslope, warm, moist flow up into the front range of the Rocky Mountains. And you're going to see convective initiation. This is surface precipitation fields that are shaded in the isosurface. And so you can see the development of a supercell thunderstorm in this region, and it'll begin to track to the southeast across Goshen County, and it drops several tornadoes along its way. So this is kind of an example of some of the things that we do. This might be difficult to see, so I'll briefly read it for you. Basically, storm chasing is essential for us as scientists to verify the results that we gather in the lab, to verify the theoretical studies and the numerical studies that we do here. We need to verify with observations. Not only do we need to verify them with sort of ground-based pressure, temperature, dew point, wind speed measurements, we also need to verify them with just visual measurements. I know that Dr. Leoff in the back over there does a lot of this work, and it's important to make sure that we tie ourselves to reality. Because we can create a lot of different numerical simulations that produce a wide variety of different tornado-like vortices. However, we need to make sure that these are realistic, and so the field is where we can verify these processes. This is the picture in the background here is actually a storm chase that we did with a bunch of students. I think it was 2016. We took out the 453 kids. They saw a tornado that day, so that was pretty cool for them, and I think it provides a lot of motivation to really go and come back to the classroom, open that textbook up, and continue the reading. Right? So it's a really good motivational tool. I apologize in advance. I've very quickly cut together, in a very poor manner, a bunch of different documentaries done by a local Fox station in Milwaukee on what we do as storm chasers in the department, or as severe weather experts in the department. And so, again, apologies, it's going to cut all over the place, but I just wanted to kind of briefly introduce what has been sort of published in the media recently with our work.
Luke Odell is a PhD student researching tornado dynamics at UW-Madison. He pinpointed Montana days in advance based on detailed analysis during what was otherwise a quiet weather pattern.
Storm chasing is really both a hobby and research, scientific research, all wrapped up in one. It's a much better experience for a student to be able to learn that way rather than say, okay, well, 15 years ago there was this tornado in Iowa.
Yeah. The storm chase trip isn't an official class. Kate Abbott and Addison Frederick volunteered their time to learn from Odell in the field.
You can tell he's very motivated about what he teaches.
See how robust that dry slow is.
Admittedly, Montana isn't part of the country you typically think of for storm chasing, but Odell saw potential for rotating storms, and Mother Nature didn't disappoint.
Whoa! Look at the mesocyclone at the base.
You got a little excited out there, you know. That's not the worst of it, but
Really did have a good chance of dropping a tornado, and to kind of like get that right off the bat was pretty cool.
This is an incredible low-level mesocyclone.
Exciting and educational.
And then the wrapping around, this is a giant volcano.
It was helpful to hear them talk about the way that these storms are forming and like all the terminology that goes along with it.
See the rain shield out here up front, the downdraft around the rear.
So, as meteorologists, we're interested in the weather.
Oh, wow.
By definition.
That's incredible.
So, of course, storm chasing can lead to moments of excitement.
This is an incredible low-level mesocyclone.
It's like, wow, you know, this is what I'm studying.
But there's also a public benefit to eyes in the field.
Great, we're getting all the wind.
There are storm chasers out there who religiously will report, you know, funnel clouds and tornadoes, and that is absolutely essential.
Oh, my God.
Odell has seen the damage storms can cause firsthand.
I remember the date was April 9th, 2015.
It's going up the foundations.
He was there in 2015 when a tornado destroyed Clem Schultz's home and sadly killed his wife. And while Schultz worries some people chase storms just for the thrill, he knows many, like Odell, have a greater goal.
I didn't think I'd be offended if he didn't do it,
Why is that?
because he's saving lives.
all a day's work, you know. But yeah, so that was just a little peek into kind of some of the coverage that we've got recently. It's been kind of good exposure for the department. I got a lot of feedback from people all over the Milwaukee viewing area, so that was
I think we probably
quite
have
cool to experience. So let's just have a brief discussion on background, environments, and dynamics of supercells so that we're up to speed. Firstly, what is a supercell? A supercell is a long-lived, intense convective storm. It is able, through the interaction of buoyancy with the wind shear that's characteristic of environments that support supercells, separate its warm, moist inflow and updraft from its cool downdraft regions. In addition to this, it generates, or is able to generate, vertical vorticity about a central axis, which allows the storm to develop what's called a mesocyclone. Basically, the powerhouse behind the supercell thunderstorm is its large rotating updraft, its large buoyant updraft. In the forward region of the storm, which is to the right in this picture, downstream, we have a forward flank downdraft, which is where a lot of the precipitation initially forms and generates cool descending air in the forward region. In the rear, as the supercell's buoyant updraft gains a lot of rotation, we start to develop what's called the rear flank downdraft, which is where precipitation is wrapped around the rotating updraft, encounters dry air, and evaporates, leading to what we call the RFD, the rear flank downdraft of the supercell. You probably have seen many of these before. This is how their supercells are best known, is the reflectivity on radar. What we can see is a classic, what we call V-notch in the radar reflectivity, owing to a diversion of the flow about this rotating updraft that I was discussing. This appendage at the back here is called the hook echo, and this is where the RFD forms, where the precipitation forms around the rear. This notch right here is the inflow. This is where warm, moist air is rapidly accelerated toward and up into the storm's buoyant updraft. So they don't all look the same. This picture on the left here is a radar scan of dodged a bullet city, I like to say, because there was approximately, I want to say 18 or 19 tornadoes from this one storm, and they all happened with a sort of 4 or 5 mile radius of Dodge City. So I just had to throw in a couple of cool pictures from that. But yeah, what I do is pretty cool. I get to show my girlfriend, who's in the back, tornadoes. I get to show my students some of the coolest atmospheric features that are out there, and I love it. And sometimes I even get to drive around in tanks like this. So that's pretty cool too. On using dual Doppler radar, we can see radial velocities, which down here on the bottom left, we can see couplets of radial velocities in the yellow circles. These indicate regions where the wind is moving very quickly in different directions. So this indicates in the atmosphere that we have rotation, and at this given time, this is what was going on underneath this storm. So these are the kind of features that we look at, study, when we go out there and use Doppler radar. I've been through this already, so I won't bark at the same tree. So in terms of the actual vertical structure of a supercell, this is the region coming in, and we're looking at it from the south. Region coming in here from the south, the flow, the warm, moist inflow is coming up, forming this updraft tower here with the overshooting top punching through the tropopause up here, and then the anvil spreading out around that. This is the forward flank region of the storm where heavy rain and hail occur, and this is sort of the rear flank region of the storm. Underneath, you can see this appendage cloud, which is known as a wall cloud, and these, most of the time, precede the development of the tornado, which you can see there at the bottom. So, the classic three-dimensional structure of the wind field associated with supercells is depicted here. This is actually going to be really important for us talking about this later on. We're going to see that trajectory analysis that we perform in some of our numerical storms closely relates to this, and we're going to look at sort of how this may lead to tornadogenesis later in the talk. So this is kind of an important picture to sort of burn into the back of your head. The warm, moist updraft, the mesocyclone, is formed here in the center, and this is the forward flank and the rear flank downdrafts here, and then you can see streams of air being wrapped around the rotating updraft and descending into the outflow regions. So supercells form in environments that are characterized by large buoyancy, so large conditional instability, and large wind shear, vertical wind shear. Right moving supercells, ones that turn right and deviate from the mean wind, or cyclonic right moving supercells, are favored in environments in which the wind profile, the wind speed and direction increase with height. So here on the right, we can see an atmospheric sounding. It's characterized by a large amount of cape, and if you look at the wind barbs, there's a significant amount of both speed and directional shear in the wind. This sets up a favorable environment for rotating updrafts. So why is that? Well, if we look at a straight hodograph or a unidirectional hodograph, this is how we plot the wind profiles with height from the sounding. And at the top here in the A picture, we have a wind that actually just remains the same, or remains unidirectional, or not unidirectional, but straight, forms a straight hodograph. So in this case, the wind shear between each height in the atmosphere is the difference between the wind at one height and the wind at the other height, right? So dVdz here, the wind shear vector is always pointing toward the east, right, the positive x-axis. So if we take the wind shear and we take the vorticity from the wind shear, we actually get vorticity vectors, relative vorticity vectors that point perpendicular to the wind shear. So if we take the flow at each height and dot it, this VH, and dot it with the vertical wind shear, we see that the vectors are never really parallel in this so-called unidirectional case, or straight hodograph, sorry. But in the case of a hodograph that curves, one in which the wind speed and direction change drastically with height, we can see that the wind shear is going to be pointed, is going to turn with height, and therefore the vorticity vector that's pointed orthogonal to that will actually have a large component of what we call streamwise vorticity. This is where the vorticity vector is parallel to the wind vector, or the velocity vector. So an important parameter that we use to decipher whether rotating thunderstorms can develop is what we call storm relative helicity. So as I described, this is the wind, the horizontal wind at each level, and it's dotted with the vertical wind shear. So at each level, we can get an integral value over some depth of the amount of streamwise vorticity in the environment. The greater the curvature in the hodograph, typically the greater the amount of streamwise vorticity we have in our environment. This means that we're more likely to generate rotating updrafts, and I'll show you why here.
It seems really hard to get a straight hodograph. You have a minimum in speed at 2 kilometers.
Right, yeah, so most hodographs in the middle latitudes that we'll see, in especially developing middle latitude cyclones, will have some component of cyclonic.
Those are a bit like that, though.
Sorry?
Those are a bit straight from 1 to 3.
Yeah, especially at upper levels, you'll see that the winds become a lot more straight, because as you say, you have an Ekman-type boundary layer, you're going to have some curvature to the winds with height, just inherently due to the surface friction. But also in warm air advection regimes, we expect to see that positive curvature to the hodograph as well, simply due to the wind shear in that environment. So the red vector here is the motion of the storm. The storm is heading to the east-northeast, and then the blue vectors at each height, this will be at the surface, 1 kilometer, 3 kilometers, these are the V minus C vector, the velocity of the wind minus the storm motion. This gives us the storm relative wind, right? The wind relative to the motion of the storm. So it turns out that the storm relative helicity could be measured on a hodograph like this between the storm relative wind vector and the hodograph, the wind profile. So this shaded region here is the amount of storm relative helicity or streamwise vorticity that we have in the environment. So you can see, just qualitatively, that if we increase the curvature in the hodograph, we're likely to get more streamwise vorticity or more storm relative velocity in our environments. This allows us to generate helical updrafts, helical flow. The picture here that I want you to focus on is down here at the bottom. On the left, we have tilting of what we call crosswise vorticity. This is where the vorticity vector is actually perpendicular to the storm relative flow vector. So what that means is that if we were to tilt via buoyant updraft the vorticity in the environment, you're going to form two counter-rotating vortices on either side of that buoyant updraft. However, if we have a significant amount of storm relative velocity in the environment and more streamwise vorticity, as that buoyant updraft develops, then the flow is going to tilt in the direction of the vorticity vector, and therefore the vorticity will form about the vertical axis as the updraft rises. So the point that I'm trying to get to here is that environments that are characterized by large streamwise vorticity are likely to develop helical updrafts, whereas on the left, if we have a straight hodograph and not much curvature, then we're likely to generate counter-rotating vortices on either side of the buoyant updrafts. This is going to lead to storm splitting. So in the first instance, in the bottom left picture, we saw an updraft generate a thunderstorm. It generated counter-rotating vortices on either side of the buoyant updraft, and that led to dynamic pressure perturbations. So the spin on either side of the updraft is causing a lowering of the pressure on the sides of the updraft. This promotes new updrafts to develop on either side, and then the storm splits. And so this is a typical structure that you'll see in a fairly straight hodograph environment when you have substantial convective instability. However, if we are able to get substantial streamwise vorticity in the inflow regions of our storm, such as we have this large looping hodograph, the flow is helical, right, as it begins to turn upwards into the updraft. And as that occurs, the flow is accelerated via buoyancy accelerations into the vertical. So that allows vorticity to be stretched about the vertical axis, which wasn't possible with crosswise vorticity. So the real benefit of having streamwise vorticity in the environment is to allow the vorticity that's being ingested into the storm to be stretched and intensified, adding to the rotation of the thunderstorm. So the key takeaways from this brief discussion here is that supercells, their updrafts are really the powerhouse, the driver behind the thunderstorm. To develop a substantial amount of rotation, they require ingestion of streamwise vorticity. And in addition, the updraft is tilting vorticity up away from the surface. So if you think about it, the vorticity that develops about the vertical axis in a supercell thunderstorm via the updraft is actually going to develop as the flow moves away from the surface. So this isn't going to bring vertical vorticity that's developing up in the thunderstorm down to the surface. To do that, we require downdrafts to bring down vorticity in some way, whether it's to generate it in a baroclinic manner, or whether it's to advect it, or whether it's to tilt it to the surface. Downdrafts are known to be essential to bring down vertical components of vorticity to the Earth's surface. And this is obviously what we need to generate tornadoes, right? And typically there's a preceding area of rotation that develops prior to tornadic generation, and these are called low-level mesocyclones. If I ever refer to low-level mesocyclones from now on, I'm referring to a broad mesocyclonic rotation in the lowest 2 kilometers of the atmosphere. So the critical thing for us to understand is in all supercells, there's precipitation, right? In all supercells, there are downdrafts. In all supercells, there is vertical vorticity that is developing at the surface underneath that storm. So why don't all supercells produce tornadoes? That's the question I want you to think about as we go forward. So a brief storm chase to show the motivation from a field perspective. This is a typical 2-day trip for us. So there's kind of 2,300 miles there, or 2,200 miles in less than 2 days. Got to get back to be that professional TA that I am, you know. But so obviously, you know, we have to drive a substantial distance to do this, and it's very much like a game of chess with nature, is the way I see it. You go out there and you try to predict the next move of nature, and it's exciting because you're able to kind of maybe one step ahead of nature, because it doesn't know that an upper level trough is about to overspread that conditionally unstable boundary there, right, or something like that. So you have to kind of be one step ahead. So on this particular occasion, this was this year, I just wanted to kind of take you through and show you some structures that we've talked about. There was a broad upper level trough over the western United States. The secondary circulation around the jet exit region is going to promote southerly low level flow into the central plains in this scenario. We've also got a large amount of wind speed shear overspreading the central plains as this jet ejects into the plains of the United States. So as I spoke about, you can see that advection taking place from the Gulf. This is bringing up really moist, warm, humid air, which is aiding in the conditional instability that we spoke about needing for development of supercells. Additionally, look at the direction of the flow, right? It's coming from the south, whereas at upper levels, the flow is nearly westerly. So we've got a lot of directional shear too. So the environment is pretty conducive for that rotating thunderstorm that we discussed. Not surprisingly then, the Storm Prediction Center highlighted a region over the Central Plains of a risk for severe weather. So obviously we were heading down to this region where the highest risk was located. The day started off pretty calmly. This was, and these pictures, by the way, are from Mr. Kirby Wright in the background, fantastic photographer, always great to have him along. So this is the initiation of a supercell thunderstorm. At first, you see very little precipitation, but you can get a sense that the updraft might be tilted. And so this is kind of the way things look as a supercell begins to form. And then this is kind of a shot through the windscreen here. Now we're looking at the base of a supercell. And what you're seeing here is the formation of what we call a tail cloud. It's what feeds the wall cloud that we discussed about earlier. It's formed from precipitation falling out into the inflow of the thunderstorm, leading to evaporation of precipitation and raising the saturation point of the air in the inflow such that the tail cloud forms at a lower altitude than the cloud base that already exists. So here's another shot a few minutes later of that same structure. There's some indication that these may play a role in tornadogenesis, and we're going to kind of touch on that a bit later. This is interesting. Now that you've still got the tail cloud here, right, and this is kind of a wall cloud, it's a rotating wall cloud. If you guys can see, just in here, there's a bit of a clearer region of air, right, where the cloud is seeming to be evaporated. This is because what's happening is air that's descending is causing evaporation of cloud, but it's rotating around this rotating updraft, right? So the air is coming in from this side and rising and rotating, and it does so, and you've got cold or cooler air relatively descending around the rotating, what we call low-level mesocyclone, right? So this would be an example of a low-level mesocyclone that seems to be pretty tornadically active because it's got a feed of this really warm, moist flow from lower levels, and then it's also interacting with the downdraft. So this is just another picture a little bit later on, and here's one where it tried to produce a tornado. This right here is a rotating wall cloud, but it got occluded by the downdraft as it spread out around. This looks a little bit better. This is about an hour later. We're getting into the evening period where the lifting condensation levels in the atmosphere drop, so the cloud bases fall, and the wind shear increases as the low-level jet begins to ramp up during the evening. So this adds to the wind shear that we looked at in the photograph, and it really increases the thermodynamic characteristics for a very short window in the evening. So this one underwent a transition during the evening into a structure that looks more like this. where again we've got this warm moist inflow, but it's surrounded by this cooler downdraft. It ended up going on to produce this, which is, it's still one of the coolest images that I've seen. And this is another one, again by Kirby Wright. I will just skip to the end to show you the orange one. So it's kind of incredible, right, how this storm can be existing for several hours throughout the day, and it can look tornadic, but it never really produces a tornado, and then boom, suddenly we've got a mile-wide tornado on the ground with winds up to 200 miles an hour.
Dominic.
We'll go over that. So that's what I use as a motivational tool for me, is seeing those structures, seeing the evolution of these storms in the field is really something that baffles me, but at the same time amazes me. And also for forecasters, right? The false alarm rate for warning thunderstorms or supercells for tornadoes is, by the last estimate, about 3 and 4, right? So given that only about 1 in 4 supercells produce tornadoes, that's not a great rate, right? So there's clearly improvement to be done, whether this is to do with our observational network or our understanding. Certainly if we increase our understanding of the dynamics of these storms and we know the features to look out for, we can improve our observational network accordingly. Another piece of motivation is in the vortex experiment that I spoke about earlier that sampled the Goshen County supercell thunderstorm. They did a composite analysis of all the storm environments that they sampled while out there. And interestingly enough, they're not very different, right? This is the sounding on the left and the hodograph on the right. They both have a large looping hodograph with a lot of, as you suppose, streamwise vorticity in the environment for rotating updrafts and a large amount of cape. There's a couple of subtle differences though in these environments. One of them is if you look on the hodograph, the non-tornadic in blue hodograph has a little bit of a kink near the surface. This is the lowest levels of the atmosphere, whereas the tornadic composite sounding doesn't. So in a study recently done by Kofram Parker, they found that the biggest discrepancy between the environments in numerical simulations was the intensity of the streamwise vorticity in the lowest levels, and the fact that it was smaller in the non-tornadic environments versus the tornadic environment. So the question is, what does that do for tornadoes, to have that additional streamwise vorticity right near the surface in a storm environment? Well, one thing it does is it enables that helical flow. As soon as it's tilted up, as I said before, it develops that rotation about the vertical axis very quickly. That's going to lower the pressure, providing an additional acceleration of the flow near the surface, a dynamic acceleration as opposed to the buoyant acceleration of the updraft, okay? So another piece of motivation for me and what we've been doing so far upstairs for the last few years is that we often use vorticity analysis to study these storms, and that seems reasonable, right? Storms need vorticity. That's how they develop their rotation, right? But the issue is we know a couple of things. One, that vorticity itself doesn't identify vortex features. It doesn't identify regions of the atmosphere that are actually dynamically balanced. And what I mean by that is it doesn't have a supporting pressure gradient. It may not have a supporting pressure gradient with it to form what we call an inertial balance or a cyclostrophic balance, right? A vortex is in cyclostrophic balance, but think about wind shear, right? We talked about dV/dz earlier. That wind shear, right, is relative vorticity, but it's not a vortex, right? Does that make sense? So because vorticity cannot distinguish between regions of large wind shear and regions of curved flow, we're at a bit of a loss because we don't know which of the structures that we see in the vorticity field are developing significant balance and which of them are associated with curved flow versus shear flow. And I'll show you some examples of that in a minute. Another aspect to bear in mind is that, as I said before, all supercells have vorticity in the lower levels. They all do, right? So why do some organize into tornadoes whilst others do not? Okay, so those are the two kind of critical things to think about there. So how do we approach this problem? Well, recently we did some work where we investigated three-dimensional atmospheric balance. To do this, we looked at what we call a divergence tendency equation, which these are, maybe I'll put it here. This is the divergence tendency equation here, or the momentum divergence tendency equation, where D is the divergence of momentum. The first term on the right-hand side here is the divergence of advection. The second term is the divergence of buoyancy. And the third term is the Laplacian of the non-hydrostatic pressure. And the fourth term on the right-hand side is the divergence of friction. And finally, we have compressible forcing. To get to this equation, what we've done is we've taken the divergence of the momentum equations and assumed some arbitrary hydrostatic reference state and removed it. Because we're not really interested in the hydrostatic pressures or the hydrostatic parts of the flow, but we're interested in the parts that deviate from hydrostatic balance. So we're looking at the non-hydrostatic forces, non-hydrostatic pressure forces here. So if we rearrange this equation, we can move pressure, which was on the right-hand side, the Laplacian of pressure, over onto the left-hand side, this del squared pi prime term. This is effectively the Laplacian of the non-hydrostatic pressure, the way you can think about this term here. On the right, we've got three terms in the brackets here. This, again, is the divergence of the advective terms. And then we've got n squared, which I've just replaced from the divergence of buoyancy, right? This is the square of the buoyancy frequency, or the square of the Brunt-Väisälä frequency. And then, of course, we've got the divergence of friction, and then the compressible term, which I've combined with the momentum divergence tendency. This term, right on the far right-hand side here, is largely involved in the compressible adjustment of the flow to the other divergence forces that you see here on the right-hand side. So between the Laplacian of the non-hydrostatic pressure and each of these terms on the right-hand side, one can develop regions of equilibrium if the terms oppose each other, right? If pressure gradient acceleration opposes inertia acceleration, you can form an inertial balance, like a cyclostrophic balance, like we see in a vortex. If we oppose the pressure gradient tendency with n squared, the buoyancy frequency, this is like a local hydrostatic equilibrium. So these are, what we're seeing here is the ability to generate balance or equilibrium between opposing tendencies in what we call the divergence equation. This differs from the vorticity tendency equation, which the vertical vorticity equation here on the top, d zeta dt, has a tilting term on the right-hand side and a stretching term. So vertical vorticity, or vorticity about the vertical axis, can develop via tilting of horizontal vorticity and stretching of vertical vorticity, right? This is how we can develop or intensify vorticity about the vertical axis. So, as I said before, the vorticity is large for both regions of wind shear and for vortical regions, or rotational flow in the atmosphere, which is why we look at the divergence tendency equation. Consider a field of horizontal vorticity. On the left here, this is some wind shear. This has got some vertical wind shear, so it's, not horizontal wind shear, which is relative vorticity. If we impose a low pressure region in that wind shear, we're going to force the flow to converge via pressure gradient acceleration toward that point. But due to the momentum gradient, we're going to get a divergence tendency away from the center associated with the inertia. So This on the right, this column here, would indicate a rotating entity or a vortex. But this is simply wind shear. So how do we use this? How do we use this equation to understand dynamic structures like vortices, and how does that help us understand supercells as it relates to tornadogenesis? Well, it turns out that the inertial field can be completely encapsulated by this term, here, I squared, which in the previous is this term. This term here, the divergence of the advection term, is encapsulated entirely by. It's entirely encapsulated by the vorticity squared, the vorticity magnitude squared, minus the deformation. So the term on the left is the relative vorticity, the three-dimensional relative vorticity, and the term on the right is the rate of strain tensor, the deformation tensor. So this includes all shearing and stretching deformation terms in the atmosphere. So it turns out that we can say that the local divergence tendency that's associated with inertia is simply half the square of the vorticity magnitude minus the deformation. So what it does is it measures a resistance against pressure gradient acceleration. If we have a divergence tendency of inertia through the divergence of the advection term that opposes pressure gradient acceleration, it's resisting the development of divergence, right? Resisting the pressure gradient acceleration. This is how we generate regions of what we call inertial balance, like cyclostrophic balance, is the opposing tendencies of inertia and of pressure. So in a very simple two-dimensional case, we can see that the divergence of advection owing to inertia, I squared here on the top right-hand corner, and the Laplacian of the pressure can exactly and perfectly balance each other. This is, again, as I referred to, a cyclostrophic balance. This is the core of what we refer to as a vortex in the atmosphere. However, if we have a region of wind shear, and we looked at the vorticity equation, and vorticity in this layer is non-zero, right? We have some vorticity in a region of wind shear. But the divergence tendency resulting from the inertial accelerations is actually zero in a shear layer, right? This is because in this layer, in pure shear flow, the shearing vorticity or the shearing deformation exactly cancel one another. In actual fact, this is a bit of a mathematical construct because in reality, there is only really just shear, right? There's not shearing deformation and shearing vorticity in three-dimensional flow. There's just wind shear, okay? Wind shear is vorticity, but it's also deformation. And so the two actually mathematically cancel in the divergence equation, and you result with no divergence tendency from inertia. However, in curved flow, we actually have, if this is a solid body vortex here on the bottom, the curved flow generates a positive divergence tendency resulting from inertia because the vorticity magnitude is exceeding that of the deformation. So an example of how we use this, to make it a bit more tangible rather than just a bunch of math, the top plot here is a vorticity magnitude isosurface. So this is a three-dimensional relative vorticity, and the second term that we plot here in B is the I squared term, the square of the inertial frequency term. And in the bottom panel, we plot the Laplacian of pressure. They're all exactly the same magnitude at the same time. And so what you're seeing here is that a lot of vortex features, as seen by vorticity, are not represented by I squared or inertial frequency. And the reason that is because a lot of these features are associated with wind shears, and they don't have accompanying divergence tendencies, and they cannot support a pressure gradient. However, there's an issue when we use I squared, the square of the inertial frequency, to define a vortex. which is a kind of where we intended to go with this, was to try to define a vortex in 3 dimensions using this term, because it necessarily implies a divergence tendency that opposes pressure gradient acceleration. So rather than it just be shear, it has to be associated with a dynamic balance with the pressure gradient. So in this case, if we have strong vertical accelerations on the right-hand side here, I have updraft plotted in a 15 meters per second isosurface, and in the panel on the left, I'm looking down from above, and I've taken the updraft away so you can see the flow. The wind barbs are a bit hard to see here, I apologize about that, but they are forming a closed loop, implying that there is a rotating entity or a vortex about this in this plane, right? So we would all probably agree that a vortex exists in this flow. In the color fill, however, I've plotted I squared. And I squared, which again is this divergence tendency resulting from inertia, is both negative and positive across the vortex. So what does this imply? This implies that the rotating updraft is not in 3-dimensional dynamic equilibrium with the pressure field. Because there is violent vertical accelerations of the flow, that if you think about accelerations in the vertical, we're providing a strong stretching term, right? Like we talked about the stretching of vorticity about the vertical axis. That stretching term is actually a stretching deformation. So it comes into the divergence equation in I squared through the deformation tensor. So it actually supplies a strain or a deformation to the flow, which renders the flow inertially unbalanced. Why is that important? Because if you think about a vortex that's growing, if it's in inertial equilibrium or cyclostrophic balance, let's say, can that vortex grow? No, it can't grow, right? There needs to be an upset to that balance to allow the flow to converge and via conservation of angular momentum, increase its vorticity about that axis. To do that, we need to supply an imbalance. And to do that, we can supply a buoyancy acceleration that provides that stretching, and that leads to a stretching deformation term that causes an imbalance in the vertical direction. So it shouldn't be surprising then to say that convective vortices tend to grow into the principal axis of deformation. It might seem a bit strange to say that because deformation is not associated with vorticity in our eyes. We're looking for where vortices form. But the stretching deformation that's applied by the updraft actually allows convective vortices to intensify along that stretching axis. And so this got us thinking, well, if I squared can't define forced atmospheric vortices, how do we define forced atmospheric vortices? Because I squared we just saw was negative in regions where the flow is vortical or rotational, right? So how do we take what we've learned and apply it and find a diagnostic that we can use? Well, I've kind of alluded this already, but we can split the flow down into 3 components about material points in the flow. The top right here is pure shearing motion. The bottom left in the figure here is rigid body motion or solid body rotation. And the bottom right is irrotational or deformational flow, irrotational strain or deformational flow. So if we split it into these 3 components, then we can define, let's skip this, a curvature vorticity term in which we remove from the total vorticity the shearing deformation in each of 3 orthogonal planes. So if we split that I squared parameter down into 3 planes, we find that in each plane, the inertial, the vorticity is half shear, right, and half curvature. If we remove that shear component from the total vorticity, we can get at a parameter that we've defined. I mean, there's other parameters in the literature that defines curvature vorticity, but it's the real curvature of the flow. It's not, the reason it's important and the reason it's exciting is because this curvature vorticity requires a supporting centripetal acceleration associated with pressure gradient, right? This term here cannot exist if I don't have a supporting cast from an opposing acceleration. So the presence of curvature vorticity defines dynamic equilibrium, right? So what does this look like in a plot? Here on the top left, we have I squared plotted, and in the middle here, we have curvature vorticity plotted. This is a time in the numerical simulation looking at a supercell thunderstorm from the south. So this is the view here. And we see an inertial balance as defined by I squared, so therefore there's a positive divergence tendency associated with inertia in 3 dimensions here, but nothing here under this feature at the surface. Whereas in the middle section, we do have a small vortex. Now this section here is curvature vorticity, as opposed to the inertial frequency. So what we see is that in some plane of motion, there is rotational flow, or flow that is being accelerated by some centripetal acceleration, right? So in the full 3-dimensional flow, it's not in balance. It's not in balance, right? But there exists some curving flow in the atmosphere at this level. So why is that? Why do we see no 3-dimensional balance, but we see curved flow? That's because this vortex is being stretched in the vertical. I've colored the curvature vorticity by I squared on the right. And you can see that where the curvature vorticity is blue, that's regions where the I squared parameter, the 3-dimensional I squared parameter, is negative, owing to the stretching deformation as a result of vertical accelerations. So the 3-dimensional balance doesn't exist yet, but we have rotational flow in a certain plane. Yeah.
So I'm curious about your thoughts of where does the idea of inertial instability end? Is everywhere where I squared is negative, is that what we call inertial instability, or is everywhere where I squared isn't 0? Is that a form of inertial instability?
It's a good question, because it depends on, I think, forced and unforced flows, because in forced flows, the flow is technically in one plane inertially stable or inertially resistant to a pressure gradient force in that plane. Yet it's being forced in the axial direction and via a stretching term, which leads to a 3-dimensional inertial instability. And that 3-dimensional inertial instability allows the growth of a vortex. But it isn't exactly inertially unstable flow if you consider planes individually. And so I don't know exactly how to answer that question, but maybe we can talk about it afterwards. So very quickly, I've got about a few more minutes to go here. How do we apply this to studies of tornadoes, studies of supercells, as it's relevant to recent findings in the literature? Well, remember I talked about downdrafts being necessary to bring vorticity down to the surface in supercells. And yet, all supercells have downdrafts, but not all supercells have tornadoes. So what is the difference between the tornadic supercells and the non-tornadic supercells? One of the key characteristics that has been identified as a possible triggering mechanism for tornadoes are these so-called warm internal momentum surges. Rather than be cold, dense outflow associated with evaporative cooling of precipitation in the forward and rear flight regions, they tend to actually appear at the lowest model level in a simulation or an observation at the surface as quite warm relative downdrafts. This is the perturbation virtual potential temperature. And you can see that the triggering surge here is relatively, it starts here, 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 relatively warm relative to the outflow around it. So the literature has found that parcels that descend into these downdrafts tend to be driven by dynamic or inertial accelerations as opposed to buoyancy, right? You think right off the bat, if you think about a supercell downdraft, you're thinking cold air evaporating, you're thinking buoyancy, right? But what we're finding recently, and this here on the top panel is parcel height descending along one of these trajectories. I think this is the pink one here. And you can see that this is the pink one's down here, the red one is this one, the southwest. It's descending along the trajectory, this path right here, toward this downdraft. The term in red is dynamic forcing, and the term in green is buoyancy forcing. In particular, note that the parcels that enter the downdraft from the southeast of the storm into that warm surge, as the parcels descend, the forcing is largely dynamically driven, okay? So we need to think about why are the parcels being driven dynamically? And so this is a better visualization than I could ever do with Vis 5D, but so this is some of Dr. Leo's stuff that we've been talking about a lot recently. This is looking at the forward flank region of a supercell thunderstorm, so it's kind of coming towards us, and the flow here is entering the updraft. I just want you to have a look at how the flow enters the updraft. So this is the cool forward flank region, and the flow entering the lower portion of this supercell updraft is being tilted and stretched. And you can kind of see the helical nature of that flow as it enters the updraft, right? Dr. Leo has termed this the streamwise vorticity current, and it appears to be of an important factor, a player in at least driving or maintaining tornadogenesis and tornado maintenance. Associated with this, we actually see, over time, I'll skip forward, we see that where this flow comes in, this is now the forward flank here, the forward flank gust front, rear flank. As the flow comes in from the streamwise vorticity current, the pressure lowers in response to that feature. So how do we get a lowering of pressure as we ingest helical flow or streamwise vorticity from the forward flank? Well, this occurs through the stretching, the tilting and the stretching of helical or streamwise vorticity, which increases the divergence tendency associated with inertia. That supports large pressure gradients that otherwise couldn't exist in that region. The way I like to think about this is, and this is one of our simulations of the same sounding, and it's not as nice, obviously. But here on the right, we have plotted this curvature vorticity parameter that I was talking about, and you can see this isosurface value here. As large as the values get in the updraft, we see very large values extending down into the forward flank region of this supercell thunderstorm. And so the way I like to think about this, or I like to explain it, is if you imagine you have a cup of water and you try to put your mouth over it and suck, you're not really going to get anywhere, right? But if you put a straw in your mouth, then you can suck, and the pressure gradient is supported by the straw, and you can actually accelerate the water up into your mouth. Similarly speaking here, in a supercell environment, if the buoyant updraft doesn't have that dynamic balance, that inertial support from the lower portion of the updraft down into the outflow region, how does it communicate its forcing, the pressure gradient acceleration, into the low-level outflow regions of the storm? It does it by creating this dynamic equilibrium or balance with the pressure field. And if we have more streamwise vorticity in the environment and augmented by baroclinic vorticity along the forward flank like we saw in Dr. Rohr's simulation, that can really support a significant dynamic balance in the lower portions of the storm that can transmit or communicate the forcing from the buoyant updraft into the low-level vorticity generation regions. So I won't see. What we're looking at here is a downdraft, and this feature here is the curvature vorticity that develops. And it seems to be associated with, this is now a tornado-like vortex that's developed very soon afterwards. The development of these features, these dynamic structures, these dynamic balances that exist in the forward flank and feed the updraft in the streamwise vorticity current appear to be related somehow to tornadogenesis. In response to that, we get, this is now looking at the forward flank again, here's this feature. Look out, this here is pressure perturbation, isosurface of pressure perturbation. And what happens in response to the development of significant dynamic balance in the forward flank is a lowering of the pressure in the lower portions of the storm. So it supports a lowering of the pressure in the yeah.
So in this, and also maybe the fourth slide you showed, there's a rippling of a streamwise inflow vorticity. And it looks like when it's rippling northward, you have less dense air because it's much moisture. Is this rippling and the timing of ingestion of moist air important for initiation? Because the moisture would help increase the pressure gradient.
Yes, I think that's right. Both by having a high saturation point flow on the sort of inflow layer.
Yeah, the orange air is going in instead of blue.
Exactly, and then on the other side you've got this cool outflow air, and so you're generating a lot of baroclinic vorticity that's being ingested into that lower portion of the updraft, and that appears to support the development of this inertial equilibrium or dynamic balance, and then that seems to play some role in tornadogenesis. So this here, again, this is a bit complicated, but what we're looking at here is a tornado-like vortex that's ongoing. We're looking from the forward flank like we were with Dr. Rohr's simulation. This is the feature along the forward flank that seems to support tornadogenesis. And this here that you saw, go back a little bit. See this region right here? This is a relatively warm downdraft pulse that seems to be associated with this structure as it develops in the forward flank of the storm. So what we did is we looked at some trajectories that enter the outflow in the Supercell Thunderstorm, and we wanted to see where are these trajectories coming from and what is causing them to descend. So on the figure on the right here, we have sort of 50 trajectories plotted coming from 3 different distinct regions into the developing tornado via the downdraft pulse. The yellow ones come in from the southeast and descend around that kind of structure, the dynamic balance that we saw in the forward flank region of the storm, and descend to the lowest model level and then into the tornado. The ones from the southwest come from a higher height, we can look at this in a separate view in a second, and descend into the rear flank, and they're not accelerated as much into the tornadic circulation, and the green ones are the streamwise vorticity parcels. So this is an animation, hopefully this will make it a bit more clear. We're now looking from the forward flank again like we were with the streamwise vorticity current that would come in up here. So these green parcels are inflow parcels, and they ascend up here. These 2 sets, the white and the yellow, are outflow parcels that wrap around the updraft and descend into this warm outflow surge, and then wrap around the streamwise vorticity parcels that are ascending toward the top of the troposphere. So what that looks like, if we plot the yellow trajectories from the southeast by themselves, they come from a height of about 1 to 2 kilometers, and as they descend into the outflow region of the storm, this again is the forward flank right here. See this warm pulse that develops as these parcels enter the updraft? They're being forced to sink into the updraft, and as a result, we end up seeing a substantial warm downdraft pulse in response to those parcels being forced to sink. We just did some basic analysis. Again, this is kind of what I was alluding to at the start. The black line is the buoyancy acceleration of the parcels along those trajectories, and the red line is the dynamic acceleration of air parcels along those trajectories. And what we find is that both can be important in different areas, but certainly to get the parcels to the lowest model level and enter the tornado, we require a really strong dynamic forcing of the flow. So that's kind of something interesting there. Effectively, where we want to take this is to use the diagnostics that we developed, the inertial frequency, and we want to use the curvature vorticity to study the communication of the powerful supercells updraft with those low-level vorticity regions, like in the forward flank, and understand how do the development of balance and the supporting pressure field that it supports, how does that lead to processes and instigation mechanisms that drive supercell tornadogenesis? Doing trajectory analysis can quantitatively help us understand how the dynamic forces associated with these structures contribute to low-level vertical accelerations and low-level vorticity generation. We aim to develop a prognostic equation for some of this dynamic balance stuff. So for I-squared or curvature vorticity, a lot of the groundwork has already been done for this. And so hopefully we can extend that and maybe predict or form a predictive equation of where curvature in the atmosphere will develop. And in addition, we want to understand the role of the stretching deformation in intensifying these vortices. As it throws it out of balance, how does it communicate the environmental forcing with the vortex structures as it grows? And finally, an interesting thing that's come up recently is studying how surface friction impacts the generation of tornado-like vortices. We've been finding in 2 different model setups that surface friction can hamper or cause tornadogenesis. And so it's really interesting to maybe use some of these diagnostics and understand how those structures may be influenced by surface friction and may therefore have a chance of producing a tornado. For example, if you have a dynamic balance near the surface, the friction may upset the inertial equilibrium, and that could expose the pressure field to the local flow environment, which may cause tornadogenesis. So there's just a few pictures of SVCs, and I'll leave my conclusions up and I'll take some questions. Melissa.
There's like natural coordinate expressions for the shear and curvature, vorticity. Have you I don't know if it's hard to calculate those or not in your framework, or have you compared?
Yeah, so those are not Gaussian independent quantities, and so when we look at curvature or balance or vortices, we want a method or a metric to do so in which it doesn't change depending on the reference frame that we look at it. So we actually, it's certainly, you're right, I think it's necessary that we probably refer to those and explain how they are different. But really this is just the true curvature of the flow as required by a continuously accelerating parcel. It needs to have a centripetal acceleration to support it, and so it kind of eludes or isolates the curvature component of the flow. Yeah.
Yeah, I was going to mention that the curvature of the flow in natural coordinates isn't really the curvature of the flow, because the flow doesn't move along an isobaric surface. The flow is moving along isentropic surfaces, right? So when you look at like a 500 millibar map and you say natural coordinates relative to the flow's not actually going along 500 millibars. It's going usually on the western side of a trough, it's diving, and on the eastern side of the trough, it's going up. So the flow is not actually curving like that at all. Whereas the way you're doing it will sort that out, and we'll get where the flow is actually curving along an isentropic surface if that's what it's doing.
Lee?
Good job, Lou. We use a term that a lot of people use. You say that the rear flank downdraft wraps around the low-level mesocycle, or wraps around the developing circulation. How can a downdraft wrap around anything? A downdraft is divergent. If you're thinking of the standard model, and I know we're in a shear environment, but say you have a pulse in the rear flank, it hits the ground spread out. How can it wrap around it?
The only way it can do so.
Being wrapped, perhaps.
That's what I'm saying.
Okay, so,
right.
but then if it's being wrapped, that puts it in it's sort of the effect, not the cause, perhaps. Perhaps, maybe, you're rapidly deepening pressure in your low mesocycle is tightening the pressure gradient up, so that any downdraft that happens to happen is going to get wrapped around.
Yes, but, go ahead, sorry.
It's sort of, it's not just you, but that terminology drives me nuts because a downdraft is divergent, it's not curved. Okay. A downdraft can't on its own wrap.
Right. Well, that's why we, with the trajectory analysis that we were doing, and we were showing that these parcels here that are entering the outflow and sort of wrapping around the lower portion of the updraft, they're doing so because they're being dynamically forced. They're not just subsiding as divergent, negatively buoyant outflows, right? So the reason the results shouldn't be so surprising, but they are because intuitively we haven't thought about that in the past. But these parcels are actually being forced dynamically to descend, and that dynamic forcing most likely comes from a supply of streamwise vorticity from the forward flank, and that as it tilts and accelerates up, that inertial balance that may develop with that helical flow may get thrown out of balance, exposing a large pressure gradient tendency to the flow around it, and that'll pull these parcels in. So yes, they're being forced to descend, and that's kind of the conclusion that I was trying to allude to with the trajectory analysis, to show that they're actually being forced to do that.
As a follow-up, then, do you need an RFG to have a tornado?
But that's so, right, so, okay, so, but how do you get the streamwise vorticity that is in the forward flank that's tilting and rising rapidly and stretching? How do you bring that, or, you know, initiate vertical vorticity or convergence underneath that to generate a tornado? Like,
couldn't it have been made way off far afield with this huge precipitation shield? You've got air that's, so you're right, you need to have downdraft to bring vertical vorticity, but couldn't it be far away and then slowly it funnels in and gets, you know, that's kind of what I see in my simulation. These downdrafts that are implicated are actually maybe far away, and then that vorticity doesn't go anywhere, it just gets streamed in.
but I wonder, so that's something that I would like to talk to you about with the surface friction, and see whether the impact to that region of the flow may detriment the sort of convergence of vertical vortices into the center. I don't know, but it'd be interesting to look at it and kind of discuss how that plays into it. It's certainly possible, but there has to be some sort of convergent mechanism underneath the updraft. So even if it's a passive player, it certainly is a player having this sort of or outflow reach the surface in the rear flank to kind of provide that convergence. Well, I guess what you're saying is that they converge underneath this large stretching of the low-level updraft. I don't know the answer to that question. I may think that's why we're still doing what we're doing, but certainly it seems that tornadogenesis, at least in the field, when looking at it physically, and in model simulations that I'm aware of in recent studies, it seems that there appears to be some type of initiating pulse. I know that your feeling is that potentially that's an effect, not a cause. And I don't know if we know the answer to that yet, but I think that it seems very significant that there always seems to be this pulse that tends to be driven dynamically and end up warm in the outflow, very close to tornadogenesis, and that's something we have to figure out.
Do you see those pulses when you don't have tornadogenesis?
The pulses that don't generate tornadogenesis tend to be very cold. They tend to be driven by buoyancy, forcing, and this is something we'll show at SLS. But they tend to reach the lowest model level very cold and very divergent. And so it seems to sort of match up. You would think then you would get cold downdraft pulses during tornadogenesis as a effect, not a cause as well. But we only get the warm ones, or at least in the simulations that we're doing, we only get the warm ones. And so it seems that there must be something there, right? But I don't know. Matt, I think, had a question.
Maybe you've explored this, but it seems like a Rankine vortex isn't too bad of a model for a tornado, where it's solid body inner rotation.
Yeah.
At the jet maximum, the tangential speed maximum, maybe I squared is 0. Maybe it's positive inside and negative outside. Is that
it switches sign.
Is that simplifying too far, or is that kind of
no? So
the starting point for
it isn't for idealized
understanding spin-up?
For solid body rotation vortices, or for two-dimensional vortices, that's fine. And you do have a core of constant I squared, and then you have a region where it transitions to negative because the deformational flow outside the vortex actually leads to a negative I squared, which means that there's no balanceability or inertial balance possible in that flow environment. But once you add a forced nature to the flow, you add that extra third dimension, and you have that acceleration, that stretching, then the problem becomes a lot more complicated, because the vortex may actually be characterized by a negative I squared in the 3 dimensions, but may have some sort of equilibrium with the pressure gradient in another plane, if that makes sense. Yeah.
I think I wanted to point out something again with your straw analogy, and this goes back to Lee's question. If you just have a straw and it has low pressure in it and you're sucking up from below, that's one thing. But if you have an updraft aloft that's sucking that straw and increasing the amount of low pressure in the straw, then as that low pressure increases, the straw fundamentally changes its relationship with the environment, because the straw is sealed from the environment provided there's a balance. But once you start pulling air through that straw and reducing the balance, the environment starts to feel that low pressure in the environment. So if you have an updraft or a flow at mid-levels or at the evaporation level going, say, moving by that updraft and not noticing it's there, when the updraft starts to pull on that straw and the pressure goes down, that becomes a centripetal force for that air moving horizontally and draws it around. That's why it wraps around. It's wrapping around because the straw becomes a centripetal force to wrap it around.
Right. So it supports the pressure gradient in the first place, and then when it's forced out of that balance or equilibrium with the pressure field,
right,
then the local flow feels that pressure gradient acceleration, and it causes a sort of convergence towards it and wraps it around. Again,
it becomes a centripetal force for the environment.
Right.
And that's why the updraft is wrapping around.
What's the tearing agent to get the straw cover off in the first place?
That's the whole point.
Like, you blow it at your little brother's head?
Well, why does it do it? Well, because it produces...
That's just making a joke.
But one of the other interesting things with this is, I think we've discussed it before, Lee, that if you imagine having a straw and then you cut a little hole in it somewhere along it, then the buoyant acceleration that's transmitted through that dynamic structure or that balance can actually locally be exposed to the environment. And if that occurs, say, in the lower portion of the updraft near the LFC, for example, where there's a huge vertical stretching, that vertical stretching is going to destroy the three-dimensional inertial balance and expose that pressure gradient to the local flow, and that might be part, at least we haven't investigated this yet, but it might be part of at least why these parcels suddenly take a turn, right? They have to be forced.
But it doesn't destroy the three-dimensional balance. It throws it a little bit out, but primarily it's still there. It could be 95% balance, but just the 5% is going to start making things wrap around it in the environment.
Yeah.
So if it was completely destroyed, then you've lost the possibility of a tornado. But if you...
No, not three-dimensional balance. If you throw it out of three-dimensional balance in the vertical...
Oh, three-dimensional, yeah, but...
Right.
But you're usually only in balance in one dimension, or two dimensions.
Right.
Yeah.
Last questions?
A suggestion? Bring a little magnetic chessboard and put it on the front of your car. For you can develop your narration. Like this is a chess. It's really a chess.
Oh, right, for chasing, yeah. Yeah, it's a good idea. I mean, we sit Starbucks for a long time. May as well actually play some chess, right?
Okay, let's thank you once more.
Thank you very much, guys.